and made assumptions.
About the homework later?
I'm sorry?
Can we ask you about the homework parts later?
Yes. There's also a hackathon tomorrow. There's a other post about it, so you can probably come there as well.
Yes. There should be a spot. Yeah, that's right. Yeah, that's got it. No, I already had sections there. Yeah, I already had some.
Okay, so we can probably start now. People, are there people on the Zoom meeting too? Someone's on it. Yeah, the recording will be posted later in case you want to do it again. So yeah, hi. Good morning everyone. So today in this recitation, we'll be covering some different aspects of optimizing your network or basically training your network. If you saw the bootcamp recording yesterday, we covered how to go through the homeworks in a logical fashion. And today we'll be covering some topics which we find really useful specifically for homework 1 part 2 and other part 2s later in the course as well. So the first aspect that we're going to be covering is data. So as you might have, yeah. I'm sorry? They haven't been uploaded yet, I think, but yeah, we'll upload them after this meeting. Okay. So as I was saying, the first aspect is data. As you might know from all the LLM hype, there are all these huge deep learning models that are trained on billions and billions of documents. So for its most part, machine learning and particularly deep learning is still a data intensive enterprise. And we talk a lot about the quantity of data mattering, I'll give you a small exercise even for your homework 1 part 2. Try training your network with 10% of the data and try training with all of your data, and you'll see a huge performance gap there. So the quantity does matter, but what also matters is the quality. Often the data that really occurs naturally is not suitable enough for throwing at your model. There is a lot of pre-processing and cleaning that is required before it can become into a form that you can actually train on. Talking specifically about speech data that you are using in homework 1 part 2, when I am just recording my voice right now, it gets recorded in the form of waveforms, which is basically the temporal variation of frequency and amplitude of speech. But that is not usable in a neural network. So what you are dealing with in homework 1 part 2 is something called Mel frequency cepstral coefficients, which is MFCCs, where you basically take a set of frequencies called Mel frequencies and you extract them at each time step, at each frame. And there is some transformation which is required to convert the waveforms into MFCCs. This has already been done for you, but there is just the other post 127 that you can look at to learn how you can perform those transformations and those pre-processing steps yourself. But as I said, you don't really need to do that because you're already given the clean MFCCs to work on in homework 1 part 2. And you will be given similar data in later homeworks as well, where you don't really need to worry so much about the data clean. If you have this clean data, what you need to do is data normalization, which you will have to do in homeworks. So does anyone have any idea why we do data normalization? Why do we normalize the features in data? Like, any idea? Okay, so for a lot of it, we do this kind of normalization to basically bring different features to the same scale so that the network does not learn spurious relationships just because of the magnitude or the extent or the range of a particular feature. So we bring all the features to similar scale so that the network can learn to give credit according to the merit of individual features. There are different kinds of normalizations that you can do. The simplest one is just dividing every feature value by the maximum value it can take, or by the range of values that the feature can take. Or there are more complex normalizations with mean and standard deviation, and you can do all these different kinds of transformations to make your data more suitable for training on. Talking specifically about speech and MFCCs, there is this kind of normalization called cepstral mean normalization, which is really important to train neural networks in a better way, because this kind of normalization helps reduce the noise distortion. So a neural network becomes more robust to that kind of a noise. Practically what you do is as I said, there are some Mel frequencies at each time frame. So you normalize each frequency by the mean and standard deviation across all time steps. There are more details in your write-up of homework 1 part 2, so I'll encourage you to read that and come up with the code itself. And it's highly recommended that you use cepstral mean normalization in your data loaders, in your dataset class, so that you can have better data to train on. After normalization, there's this concept of augmentation, which literally means increasing the amount of data, because often you don't have so much data to train on. I think the most intuitive way to think about normalization is to think about images. If you have this one single clean cat image, but you don't have a lot of data, there are ways to create more cat images. You can basically flip it across some axis, you can introduce some blurring, jitter, or you can even invert the color scheme in a few of them. What this does is not only increase the amount of data, but it also acts as a kind of a regularizer, because now your network does not only know how to predict on super clean cat images, it also knows how to predict on lower quality and differently oriented images. So I'm sorry, yeah.
Sorry, I didn't mean to interrupt. I was just wondering, like, do you use the original image and the modified image in the training data set, or do you use one or the other?
No, we keep all of them. So in practice, what we do is we have a set of augmentations that we keep in a part of our data loader or dataset class. And at the time when we are loading an image, we have some probability according to which we apply the augmentations. So in every epoch, we either load the same image or we load some transformed version of the image, which is a combination of all these different augmentations. So as I was saying, in effect, we would be regularizing the network too by doing this and getting away from overfitting to some extent. You don't really need to do data augmentations in the first homework because the cutoffs have been set such that you can easily clear them without the augmentations. But if you still want to do, Then for speech, there is this kind of a masking that is done for MFCCs. So there are two axes for MFCCs, the frequency and the time axis. You can mask along either of those axes and do augmentations. These are slightly expensive to do, so you can't really plug them in directly into the starter code that has been given to you. But if someone's curious how to do them in homework 1 part 2 itself, you can probably come to some office hours and we can see how we can change the code to do these augmentations efficiently. But as I said, you don't really have to do them in homework 1 part 2 to clear the high cutoff. All right, so once you have all this clean, normalized, augmented data, you need to throw it at a network, right? And arguably the most important part of a network is the architecture of the model itself. And it's in fact one of the most painstaking experiments to be done, because unlike other things like learning rate, regularization, etc., you cannot make a very theoretical argument as to why one architecture works better than the other. So there is nearly no way of predicting in advance that one architecture will be better than the other. You have to perform those ablations, which are obviously time taking. So we'd really encourage you to split up architectures in your study groups and perform those experiments in a distributed fashion so that you can cover a large variety in the same amount of time. There are quite a lot of architectures, but from the first couple of lectures, you might have this intuition that in general, deeper and wider networks have more representational power than narrower and shallower ones. That is mostly the case, but you have this limit of 25 million parameters in homework 1 part 2. So you can't just create a huge network of 100 layers, each layer having 8,000 neurons. That is just not feasible. So you will have to do some ablations on architectures within the 25 million parameter limit. So there are different shapes that you can try.
A comment about the deeper models equals better performance thing. Even if you didn't have the 25 million parameter limit, like let's say you can have as many parameters as you want, that does not mean that the largest model you have will be the best, because you're also limited by the data you have and also the representation power of the structure of the model itself. Even if you have, let's say, a MLP, like multi-layer perception, which is what you're doing this homework, there is no way that that will be more competitive than, let's say, than some of the later structures like CNN or LSTM or those things, right? So you're limited by that also. And so yeah, deeper models always are better than shallower models, but provided all the other things are the same, which does not say this.
Yeah, you are definitely limited by the amount of data that you have. So if you just get your hands on a bigger data set, you'll probably see the effects of a bigger model, but not otherwise. All right, so as I was saying, there are different shapes in terms of the layout of neurons that you can try. These are some common ones that we've listed here, but you're free to try other ones as well, like diamonds or two pyramids, or you can just stack up similar layers next to each other in the form of a cylinder or some weird shape that you want. But yeah, do try these different architectures, see what works out for your problem, and as I said, please distribute them amongst your study groups. Apart from the layout of the neurons and layers themselves, there are also other factors to take care of when you look at the architecture, like the activation layers that you're using. They're pretty useful, as you might see that if you use like a sigmoid or tanh, you might run into problems of, say, vanishing gradients if you go into deeper and deeper networks. But there are ways to mitigate that by using things like ReLU and GeLU. So there are some activations that you can try. You can also have some regularization layers, which we'll cover in the next few slides, like dropout layers. Really recommend you to use them, particularly after the wider layers. You can have batch normalization layers and things like that to make training more stable and slightly regularized. So there are all these different things that you should try and consider when you're creating your architecture. And you should definitely include a lot of these things like dropout and batch normalization, but do everything within the 25 million parameter limit. After this architecture ablation, there is another pretty annoying thing, which might not seem like it makes a lot of difference, but it does, which is hyperparameter tuning. So hyperparameters, what is the difference between parameters and hyperparameters? Can anyone tell me? Does anyone know what is the difference between a parameter of a model and a hyperparameter?
Hyperparameter is
Yeah. So when we say parameter, we mean the weights and biases of a model that are learned by the model during the training cycle. Hyperparameters, on the other hand, are values that you just set, which control the behavior of the training and inference cycles. So there are things like the learning rate, the amount of regularization that you're using, the dropout probability, even the optimizing algorithm that you're using, and things like that, which remain constant, but they control how the training behaves. You will have to do quite a bit of hyperparameter tuning specific to your model architecture and data. So yeah, once again, that is something to be split in your study groups. We'll now cover some hyperparameters that are really important to perform ablations on. The first one is learning rate. So when you start with a network and an optimizer, it's really recommended to come to terms with a decent enough learning rate, which is not too slow that your network starts crawling, and it's not too fast that your network just diverges, the training just diverges. You will be learning about convergence and divergence in a few lectures, I suppose, and the importance of learning rate in connection to that. But learning rate is basically, you can think about it as the amount of difference that you make to the weights at each training step. If you make huge steps, then your training will just diverge, your loss will just diverge. And if you make very small steps, it will take a lot of time for the network training to converge. So learning rate is pretty important, and it is highly specific to the optimizer that you're using. But a constant learning rate throughout the training process is not good enough, because consider the first epoch when your network has not learned anything. You might want to keep a pretty high learning rate then. But after your network has learned quite a lot and it is very close to its lowest loss possible, you'll not want to make very huge strides in your weight changes, because then you might just go away from the minima that you're on. So as a practice, we generally decrease the learning rate over training. And then there are different algorithms to schedule this learning rate or decrease the learning rate. You can look at PyTorch's options of learning rate schedulers. There are things like reducing the learning rate by a constant factor every few epochs or every epoch, or you can even connect your learning rate to a metric like validation accuracy, which is often very effective, because you only reduce the learning rate if that metric has plateaued for a certain number of epochs. So that is another learning rate scheduler that you can look at. And there are different others. Some of them just reduce the learning rate according to a cosine schedule. And there are all these different algorithms that, and some of them are plotted here, so you can just linearly reduce or in a stepwise fashion or a cosine fashion. But do look at the PyTorch documentation and try your hands out with some of these different scheduling algorithms, because these will be very useful, particularly in the latter part of your training when you need to play around with the learning rate, adjust it for the model to converge or move to a better minima. Did you say something?
What's that?
Did you say something?
No.
After that is the optimizer. It's kind of in the reverse order. I'd actually recommend you to reach a good optimizer first before you do the learning rate ablations, because learning rate is very dependent on the optimizer. So if you are aware of the training of a neural network, which I think you have already started in the lectures, so after you do the forward pass for the simple NLP, you first do a backward pass to compute the gradients with respect to all the parameters, the weights and biases of the network. And once you have all the gradients, you use those gradients to update the weights and biases. The update step is where the optimizer comes in. The optimizer controls how you use the gradients. Do you use the average of gradients, running average of gradients, the gradients themselves, or how you use the gradients to update the weights and biases. So the optimizer or the optimization algorithm is another pretty important thing to come to terms with. Some of the most common ones that are used and that you will be using in the homeworks are stochastic gradient descent and ADAM. And I believe you are also implementing SGD in your homework 1 part 1 and ADAM and a variation of ADAM in homework 1 bonus. So you will be pretty familiar with the theory by the time you get through homework 1. And I think there is also a lecture which focuses a lot on the different kinds of optimizers and the theory. So again, please pay attention there as well. But there are not just these two optimizers, there are a lot more of them, which are somewhere between ADAM and SGD. Like they are some sections of ADAM, like the RMS prop is some part of ADAM, then momentum is also in a sense some part of ADAM, so you can play around with all these different optimizers. Like just talking about two of them, so SGD generally gives you a better minima, but it's slower and slightly more stochastic and it's slightly more noisy, the training. But Adam generally converges in a more stable fashion. But yeah, you can get some suboptimal minima there. So again, this is something that you should play around with. There are some theoretical points given here that you can read at your own leisure time. Finally, coming to overfitting, this is something that you will definitely observe in all your homework part 2s, especially when you're reaching very close to the high cutoff. So say in homework 1 part 2, you reach 84% validation accuracy, and then from there on, you'll see that the validation accuracy keeps coming down, even though the network seemingly keeps learning. So overfitting is a phenomenon where you learn the data sets, the training data sets behavior so well, your network learns it so well, that it kind of loses or it diminishes its generalization power. So its performance on a held out validation dataset keeps reducing even though the training accuracy is still improving. So it's just learning the behavior of the training dataset. And this is an even worse problem when the validation dataset is of a different distribution than the training dataset, which often occurs in the wild. So you have all these methods of circumventing or reducing the amount of overfitting that you're doing, and they're generally referred to as regularization. So if you remember, we talked about dropout during our discussion on architecture. That is also a popular method of regularization. But in its most basic form that you would have learned in an intro to ML course that you must have taken is standard L2 or L1 regularization, where you penalize the magnitude of the weights according to the L1 norms or the L2 norms of the weights and biases. If you look at PyTorch's implementation of this, if you look at the optimizers like SGD or AdamW or RMSprop, there is a parameter called weight decay. So the weight decay is the equivalent of L2 regularization. So if you want to play around with that parameter, weight decay is something to look at. And it is definitely very important to get stable and less overfitting training. So once you have an optimizer and a decent enough learning rate, please freeze a good enough value of weight decay that you can sustain with through the rest of your ablations. After you do this L2 regularization, there is some more advanced regularization, which is called dropout. So dropout is also something that you will be implementing in homework 1 bonus. Dropout basically means that if you apply a dropout layer at, say, the third layer of your neural network with a probability of 30% dropout, then at any training step, you will only be considering 70% of the neurons at that layer. So in effect, what this does is, at any training step, you are only considering a small section of your network. So never are you acting as if you have a very huge, complicated network. You're always acting or mimicking as if you have a smaller network, a sparser network, and the actual neurons that keep getting dropped keep changing over training cycles because they are randomly picked according to a uniform distribution of the probability that you specify. So over the course of training, you will learn weights for all the neurons, but at any one particular training step, you won't be training all the neurons. Okay? So this is something which is very effective, and you should consider adding dropouts after the wider layers because those are where there is the most complexity concentrated. But yeah, play around with the probability. Generally, probability less than 0.5 is pretty effective. But yeah, do play around with those things. I think that's pretty much it. So, yeah.
I hope I can just take over here.
Do you have any doubts up to this point? Okay. So
Alright, cool.
Josh will take over.
Question?
Oh, there's a question
There's a question.
on Zoom? And what is it?
Yes. Can you hear me?
Yes.
Yes, about the dropout, I have a question. You said that for a specific function you want to learn with deep neural network, there is this kind of how the minimum hidden layer we need to have, or the minimum neuron we need to have it, if maybe it's just one hidden layer. Now, when we do the dropout, we are removing maybe some neuron for our processing. So how do we know that after removing this neuron, the remaining neuron could process our function to give it the expected output?
Question is about having dropout for shallower networks. Is that the question there? Is
Do
the
you
question
get me?
about Is the question
Yes.
about the effectiveness of dropout in shallower layers, in shallower networks?
Yes.
So dropout, just like L1, L2 regularization and things like that, is a way of preventing overfitting. So if you're using particularly shallow networks, it might not be very useful because you might just converge very quickly and you might not see overfitting very quickly. But what you can try to do is first train your network without dropouts, create an architecture without dropouts, just keep it all the linear and activation layers and batch norm layers if you want to. Train it and see if it starts overfitting. If it does start overfitting after a particular point, which it might if you are using, say, 10 or 12, even 10 or 12 million parameters, it will start overfitting at some point. Once it starts overfitting, then maybe start adding some dropout starting with the wider layers and see if it prevents overfitting or delays overfitting. But don't start off with dropout immediately because otherwise you might just slow down learning for no reason. And that can happen in the case of already less powerful networks like the shallow networks that I mentioned.
Okay, thank you.
No. Are there other questions up to this point? Cool. If no questions, we'll move on. So here, really, what we're talking about is a bunch of tricks that you can think about, keep in mind, and add to your network of one part two, right? So we have optimizers, schedulers, dropout. So these things that we talk about them conceptually, like we just talk about what they are and what they do. But in the end, you want to use them in PyTorch, right? So what you do is literally just Google the name space PyTorch, and then it's usually very easy in terms of plugging them into a model. It's literally just a one line that you can just Google. All right. So weight initialization. So what it is that when you specify a model architecture, let's say you use up all the however million parameter limit that we give you, and you specify one of those weird shapes that we show in one of the earlier slides. But then the question is, what are those values for those parameters in the weights and biases before you do any training, right? So it turns out that, first of all, you don't want the initialization to be uniform. You don't want them to be all zeros, just because if they are all zeros, then because of some weird math, then all of the parameters in the network later on will not be any different from each other. And you don't want that. And so then you might want to think that it doesn't matter because of whatever you initialize those values to, it'll generally converge to the minimum, but that's what you think. Really, initialization is important to where the network ends up, just because if you think about it that way, I can't really draw them here, but if you have like a valley, right? You've seen a lot of those in professors' slides. It really depends on whether you are spawned to the left or to the right of the valley, because you generally go downhills, right? But then the minimum, let's say it's kind of those one of those locations that's in the middle. You want to be spawned in the same valley as that minimum to be able to go downhill to there. If you are spawned a couple hills apart, then you will go downhills to somewhere else, right? So this is what weight initialization is about. And it turns out that there are a lot of pre-built initialization schemes. Xavier, Chiming are the two that are the better known. And then you also have Uniform and Gaussian, which is just a way of saying using a normal distribution for that. These things, you might think that the more sophisticated, the better, but really, as we said, as with all things in this homework or in deep learning in general, you got to try it out. You better know whether it actually works. So again, these are also one-liners. You can plug them in, and you can just see, how well it works, right? All right. So that's weight initialization. And now there's another technique which is called batch normalization. And the motivation there is that if you feed your training examples to your network mini-batch by mini-batch, then some of those mini-batches will have different distribution properties than other mini-batches. So as it turns out, chance takes it so that maybe there's a chance that some of your most extreme examples would end up in one mini-batch, and your network will just learn that, oh, this is what your examples look like, when in fact it is not, right? So you want to normalize each batch so that they look like each other in terms of distribution. So then you can actually trust that your network learns a global representation of your training examples instead of any local, luck-based representation of a subset of those, right? So what batch normalization layer does is it takes in a batch and it literally subtracts the, where is it? It subtracts the mean from it and it divides it by the standard deviation. So it does normalization, right? And then it does the other weird thing, which is it performs a linear transformation on that. So it multiplies that by a weight and it adds a bias onto that, just so it has some representation power of the training examples that you feed it in one mini batch, so that they don't look exactly like each other. So this is a good idea. You should try it. It usually helps with a lot of things. It helps with convergence because the network will not struggle to jump here and there and learn different training examples separately. It will learn all the training examples in the same capacity because they will be generally over the same region in the internal coordinate system in the model. So then the model will actually converge faster. It will also help with mediating overfitting, as it turns out. But then the general good idea is that you should try it out, right? As with always. Here it is. It helps with faster convergence and regularizes the models. Cool. So there are other techniques that you should try out. We're mentioning them here. What happens in the end is, I'll mention in the end that you need to have a ablation sheet, what we call ablation sheet, and then you need to divide these options to try out with your teammates, because usually it's less feasible to do all of these things, to explore all these options by yourself, right? So these are entries in the ablation sheet that I'm gonna bring up in a minute. So early stopping is literally, you can just from the training console, you can see how much the loss is, how much the accuracy is, and then you can kill the training, right? And also you can just literally save a checkpoint every now and then, so it doesn't really matter when you actually stop the training because you'll have checkpoints from earlier. Gradient clipping is another thing you can add on. So this is actually pretty interesting and it's going to be useful for you because in previous semesters, I've seen a lot of people, especially during homework 1, that their loss goes to NaN, to NaN, which means not a number. And the reason for that are twofold. There are two possible reasons. There are actually a lot of reasons, but then one of the reasons is that the gradient is too high. And the gradient is so big that it exceeds the range of the whatever the floating point type you're using in your particular program. So what you're going to do is you need to apply gradient coupling. So what this does is when the gradient is larger than the threshold value, you just keep it at the threshold value. So it does not upgrade the model by too much, because otherwise you keep propagating layer by layer down, and the later it becomes, the larger it's going to be, and in the end you're going to have a NaN loss value, which is not what you want because the model cannot train that way, right? So here you need to also have what's called mixed precision training, and this has to do with torch data types. This is one of the more painful parts of PyTorch because I don't know about you guys, but for me personally, I chose machine learning as specialization in the broader realm of CS, just because I can stay away from the computer systems part, like how many bits are used for each integer and floating point and stuff. But then here it comes back to you, right? So what happens in here is there are a range of data types that you can use in PyTorch, which is kind of counterintuitive if you think about it, because you would think of PyTorch as this very high level programming language that it doesn't really concern, it shouldn't concern itself with how things are implemented, because if you think about it, you have all of these fancy ideas, right? Batch norm, weight initialization, and all of it is just one line. So you would expect that PyTorch will stay away from, how many bits are used for your data type. But it is actually pretty important because it depends on how precise you want your model to be, and also it has a implication on the amount of memory that you use, because literally FP32, which means you use 32 bits for your floating point, is twice as big as FP16, which means you use 16 bits for your floating point. And so the way that floating point works is that, first of all, have Any of you have taken computer systems, 213, 513? All right, some of you, right? So for those of you who have taken that, you will know this, but I'll explain this. So what happens is that in a floating point, especially at least in the classical, CS point of view, you have a mantissa, you have a exponent, and the sign, right? So the most important part in that floating point is the exponent, because it dictates how big the range is that your floating point can represent, right? If you only have 2 bits for the exponent, then the most that you can take the power to is you can take something maybe to the 3rd power, to 2 to the 3rd, which is not a lot, right? So FP32 is actually way bigger than FP16, just because there are more bits to the exponent, right? It's not twice as large, it's many, many times as large. So if you use FP32, there's less a chance that your loss will go to NAND. You need to know this, because all of you not all of you, a lot of you are gonna go to office hours saying, hey, my loss is NAND, what am I gonna do? So here's the answer. You're using FP16, or you're not doing the gradient clipping, right? So if you use FP32, there's less of a chance that your loss will go to NAND, but your model is also going to be twice as large. And that's probably not going to be an issue with this homework, because we're not building production software. You're just training a MLP on a bunch of audio. But you still need to know this, because in actual machine learning jobs, it's actually pretty important, because all the models are going to fit not on one GPU, but multiple. And then you want it actually to be as small as possible, but still, do what you want it to do. So yeah, so there is a way to set these in PyTorch. Like, all of the things we talked about so far are not very complicated. These are literally one-liners. You need to Google it. I can't recite it right now, but then there are 2 ways to set the data type in PyTorch. One of them is you need to set I think it's something called torch default D type. You need to say that is FP, either 16 or 32, whatever you want it to be. And then the other thing is, in your model, when you take in the data, you can use the .to function to convert it to a certain data type, which is very easy, right? So just so you know that these things we want you to do are not too fancy. You just know that they exist and try them out, that's all. Okay. So, yes.
Is it an issue, so like, let's say you switch to 32 and grade is wrong, now you don't pay that, but is like having a huge gradient an issue? Like, does that indicate something that how your model will perform, or? I don't know.
Right, good question. So a large gradient, like a huge update, is generally, when you think about it conceptually, like from the slides that we have read in lectures so far, like you would think that's worrying, because you might jump over and you might just miss the minimum, and that is true. But then that's also not something that you can control if you have the data, and you can't just take out individual pieces of your training data to make the gradient smaller. No, that's not an option. So if the gradient is large, it's large, like that's it. But then you need to have a data type that can hold that gradient instead of breaking your backprop.
And sometimes a large gradient might just be the result of very poor weight initialization. So there are some weight initializations which for some architectures can just throw you or spawn you at a very bad place, from where the loss is so high that first of all you get an AND loss and the gradients are way too high. So you can also try changing the initialization.
Cool, I'll go on. So also feel free to ask any questions at any point. Oh, yes.
How do you figure out the threshold for gradient?
Clipping?
Yeah. What does that do for you?
So I think this one, the few times I've tried it, you just try out as with many things.
Right.
Yeah. I think there might be a better answer, but I'll put some PS about it. Other questions? All right, cool. So yeah, here actually we have the commands that you want to insert into your program if you want to do mixed precision training. And what this does, oh yeah, I just went on and talked about how FP32 is different from FP16, but then here what we want to do is actually mixed precision training. So what it does is that you actually store your model in 32, which means it has higher precision. But during training, you use FP16. That's what it means by mixed precision training. And the advantage of that is that during training, because, okay, think about it. During training, you want to keep 2 copies of each parameter. in your model because you want to have the original value and then you want to have the updated value, right? So during training, the training process is actually more costly in terms of memory than just storing the model. Okay, so when you use mixed precision training, it actually, one, is faster, two, it actually saves the memory. And I don't know whether memory is a consideration here, like how likely it is that your model is going to overflow to the GPU that you have access to, which is probably going to be in Colab. But then, yeah, if you want to do what I just said, mixed precision training, this is what you do, right? AutoCast. Okay. So now we have come to the fun part of dividing up tasks and telling your teammates to do things that you don't want to do. So weights and biases is something that we recommend. I think it is in Recitation 0. You should have watched it. So this is a website, a platform that helps you keep track of your model ablation runs. And by ablation, I don't think we've explained that term too clearly. Ablation means trying out different options, right? So you can see this is what it looks like. If you have actually practiced the assignments in Recitation 0, then you probably have made an account and tried out all the things you can do on the website. So during training, you can log down your statistics, which means your loss and accuracy and whatever that you want to log down, and they can paint you a pretty graph like this. And you can keep track of what different options are being explored. And there are also, so these are the basic ones, right? And there are also more fancy things that weights and biases can help you do, which is called hyperparameter sweep, which means it can literally do all the exploration for you and then pick an option that's the best. But then that's actually more complicated to set up and get running. So then that is optional. You can explore that if you want, but if not, you can manually create all the runs and log down the results so that you know which option is the best, right? So what we recommend you to do is, since there are so many options, right? So let's say what I talked about so far. With initialization, there are like 4 options. Batch norm, there are a lot of options. So batch norm is, the choice there is not really binary, like with or without. It's where you insert it. You can insert it in any location you want, which basically means there are infinite number of choices. So then the decision tree explodes there, right? You can see. So you can only explore part of the tree and not the entire tree. And then you want to do it with your teammates, study groups, which hopefully you will have by this week. So you need to have, what TAs do is we have a Google Sheet, and then we randomize a portion of the decision tree, and then we assign a couple of the options to each person so that they can run it and log down the results in one column. You can compare that column to see which architecture is actually the best. So use weights and biases, work with your teammates, and here are some other tricks. When you try out, as I said, try out the option of like a certain architecture or a certain activation or whatever, right? You want to do that in a subset of the training set. You don't want to do it in the entire training set just because it's less time consuming to do it in a subset, and also just because it's actually not what you want your model to seriously to be. It's just an exploration, so you want to do it as fast as you can. So, but you also don't want it to be too small because then it might not be representative. So you want to have a small enough, but also big enough subset of the training set that you do those ablations on. And when you finally find the best architecture, you run that on the entire training set. Okay, and these are just some kind words. A huge portion of the time I just be looking at a screen and worrying about training exploding. So then there's no way around it. If it explodes, try all the things that we said earlier. Also start early. I think it is mandatory for you to make a submission with before the early deadline, which should be very trivial. You just need to run through all the code. So do that early. And there will be a medium and a high cutoff, but then those won't be unrealistic because when we release the cutoffs, we are going to be confident that that is attainable, at least by one of our runs, before we release the cutoff. So know that those are definitely doable. It's just you need to do enough ablations to find the right architecture for it. Also, shuffle the training data set. It makes your model more robust, but do not shuffle the test or validation set, because if you shuffle the test set, then when you submit on the Kaggle, the labels that you submit will be in the wrong order and you have a very low score. So do not shuffle the test set. It has happened earlier. Batch size, learning rate, all the hyperparameters, choose wisely. And yeah, explore ensembling. So what ensembling is, we're gonna have a different recitation on this. So here's just a spoiler. So what ensembling is you train, basically you train a couple of models, let's say 4 or 5, and then when a new, not training, but testing example comes in, you feed that example to all of your models, and they will each produce a label, and you just do a majority vote in all of your models there. So that's called assembling. If you have taken a other, like intro to ML class and to tell you about random forest, this is what a random forest is. So experiment with schedulers and collect your garbage collection and empty your cache every now and then, basically in each epoch will be nice, because then you won't run into memory issues.
Just a small thing. So it might happen that sometimes you begin training and you realize, oh, sorry, I messed up, and you just do Control-C and stop your training. So if you do that kind of a combination of training, then PyTorch will not do the garbage collection for you. It will not free the GPU memory. Your model, your batches will all still reside on the GPU, and if you restart training, it's highly likely that you run out of GPU memory. So always run this command after you stop training and have this, and I think it's already there in your training loop as well. But if you do terminate training manually, you should run this command. Please do it.
All right. So ensembling and and the way that Torch works is that you need to explicitly say Torch like model.train or model.eval. And the name is kind of misleading, because when you say model.train bracket bracket, it actually does not mean train your model. It just means put your model in training mode so you can actually train it yourself, right? And when you eval on the model, you need to put model.eval, or you can use torch.inference mode. These things are the same. And the reason for that is you don't want the model to accumulate gradients on the kind of examples that it receives, so that it saves memory. So do not forget to put in these commands that we put up here, and and empty cache and collect. We talked about that. So here are some other notes that you can read on your own. The slides is going to be available to you. I don't think there's too much to say about these. If you get CUDA errors, run on CPU, although sometimes it's slow, it's up to you. And then, yeah, you can read this. These are very self-explanatory. And the other parts are more important.
One thing about the previous slide.
What?
The previous slide. So about the number of workers for data loader, I think it's the next one. First point. So if you're using Colab or Colab Pro, it might work with a large number of workers. But if you're using GCP, you might see running out of memory when you're creating a data loader. So you might want to reduce the number of workers to an acceptable level, because the way GCP is now, it takes memory from a shared quota of memory, which causes problems at busy times. So you might want to reduce the number of workers if you see that kind of a problem in creating the data loader itself. There is a parameter for number of workers when you create the data loader.
All right. So here's a meme. Thank you. That's all. All right. Time for questions.
Please. Yes, can we have this recitation sheet on the website?
Where's that?
Yeah, we'll have.
Can you hear me?
Yeah, we'll have the slides uploaded on the website.
Okay, thank you.
All right, that's all we have.
Another thing about weights and biases, so weights and biases also enables you to log models for every run. So I know you will be logging models on your local machine, on your GCP VM or whatever, but do log models to weights and biases as well, because you might just stop your GCP VM to save cost. And when you try restarting it, that zone might just not have enough resources to spin off that VM. So you might just lose your VM completely, and you will lose models if you're not logging them elsewhere. So do log models locally, but do log models to the VM, but also log models to weights and biases, so you have like a backup bookkeeping or whatever you might call it.
All right, if you have questions, either raise your hand or come down here, so we have to, or post on Piazza.